The question to start off this lecture is, how are you seeing this slide right now? You might answer me very simply, with my eyes. You might have a slightly more complex answer, like my computer screen is emitting light that I then register through my retina. There are many ways to answer this question, but hopefully in half an hour you'll be able to answer this question with a little bit more depth and complexity than you can right now, or at very least do so in English a little bit better. So today, as you probably guessed, we're talking about light and vision because they go hand in hand. In order to understand how our eyes work, we have to understand what kind of input they're getting. I think it's important to cover light and vision because vision is the primary sense that we use to interact with the world. It also provides a good example of a system that takes an input and then needs to continue being regulated. So it operates differently than the other homeostatic mechanisms that we talked about, or like the physiological mechanisms that we've talked about. It's not about keeping your body safe or at the same level as it should be. It's about gathering information from the outside world. So this week we're doing light and vision, and next week we'll be doing sound and hearing. So what is light anyway? As you probably know, light is excreted in these discrete quanta called photons. So there is a light particle. It is separate than the subatomic particles that we've already talked about. So it's not a proton, neutron, or electron because they don't involve atoms. So they can interact with atoms, but they're not atoms themselves. That does lead to the kind of tricky situation. Then light isn't really matter, which is an interesting debate to get into. Speaking of debates, it was long debated if light traveled in these discrete quanta, in these discrete packages that can be transported, or if they were waves, so the same way that we know waves of the ocean or sound waves. And the answer is it's both. So light is both a particle and a wave. It's created by this oscillating photon electromagnetic field. So you have an electromagnetic field coming off of a wave of light that is oscillating up and down, so going up and down like this. And so it's creating an electron field one way, electric field one way, and a magnetic field the other way. So we're not going to get into the specifics of this. This is not a physics class, but we are going to talk about two of the types of ways that we talk about graphs, and specifically how that relates to light, and we'll eventually talk about it related to sound as well. So here is a graph. This is just a normal sinusoidal wave, and when we're thinking about a graph, a couple of the things that we want to think about, a couple of the ways that we can describe it are through its amplitude. That is how far it is from this axis here, the x-axis, to the crest of a wave. And so in most cases, this is the same. So from the crest of the wave to the dip of the wave, these are the same. And so we're only looking for one half of this. So from here to here, this is the amplitude. And for light, this indicates how intense or bright a light is. So the higher the amplitude, the brighter the light is, the lower the amplitude. So if our wave, for instance, looked like this, the lower the intensity of that is. Wavelength of light is correlated to color. So longer wavelengths of light are correlated with reds and oranges, and shorter wavelengths of light correlate to purples and blues. There's another way to think about this as well. So wavelength is inversely related to frequency. And so frequency denotes how many times from here, like how quickly this wave passes the x-axis. So how many times in a given bit of time does the wave pass the x-axis? And this is inversely related to how long this crest-to-crest length is. Because the longer the crest-to-crest length, the longer time it's going to take before it passes again. So high frequency means low wavelength, and low frequency means high wavelength. So you can think about it in either capacity. So either purple has a short wavelength or a high frequency. We could also think about it as red has a long wavelength, but a low frequency. It also gets a little confusing because we describe frequency as high and low, and we describe wavelengths as short and long, because they're lengths, right? So it can be a little confusing, but hopefully that straightens it out. There's also a speed of light, and light always travels at the same speed, which is 3 times 10 to the 8th meters per second. That means that to make it the about 93 million miles it is between us and the sun, it takes about 8 minutes to travel. So light travels really fast. You know this from sci-fi movies. So as we said before, the color of light is associated with its frequency. The longer the wavelength, the more you're getting to reds and oranges. The shorter the wavelength, the higher frequency. You're dealing with purples and blues. And wavelength is also inversely related to increasing energy, which means that frequency is positively correlated with increasing energy. And so purple light has more energy than red light. And this is going to make a little bit more sense when we think about this in the context of a larger electromagnetic spectrum. So just to reiterate one more time, for low frequency, we have red, and for high frequency, we have purple. So color is related to either wavelength or frequency, however you want to think about it. So you can also think about this as long wavelengths and short wavelengths. Hopefully you can tell the difference between these two colors. We have low amplitude, so this kind of duller color, this less intense color. And we have high amplitude, this more intense color. So just to point out, these two have about the same intensity. That was the hope. And they have about the same amplitude, even though they're different colors. They have different frequencies, different wavelengths, but they have about the same amplitude. They go up and down about the same amount. And similarly, these have the same wavelength or frequency. They're just upside down. So you have this dip, but they have the same wavelength or frequency, but they have really different amplitudes. They don't go up and down off of the hypothetical x-axis as much. So this is why these are both reds, and the former two were the same intensity or brightness. So to think about this situated in the larger electromagnetic spectrum, visible light is only a little bit of what we can see. So visible light is located right here. And we can think about a lot more things that operate in this way of electromagnetic waves that we can't see. And so anything that has a higher energy and a shorter wavelength than visible light are things that we can't see. We can only see in this very, very narrow range. And so those are things like gamma rays, X-rays, and ultraviolet rays. We can think about this as ultra. Ultra means above, so it's above violet in our frequencies. So, and we can also intuit or understand without being told necessarily that these are high energy. So things like gamma rays, which come from really intense radiation, X-rays, which come from radiation. Again, they're very high energy. And these things can both penetrate the skin. Ultraviolet rays get caught in the skin. This is the concern that we have around too much sun exposure, because they get into the skin and they begin to alter the cells that we see there and can be cancer causing. They're carcinogenic. When we talk about lower frequencies and longer wavelengths than light, we have infrared, which we use, for instance, to do heat mapping. We have radar that we use in the oceans, TV, FM and AM radio. You guys might not even remember AM radio. And so these are all have very low energy, and meaning they, as waves, don't penetrate nearly as much. The same way that we have ultraviolet, we have infrared. Infra means under, so it's a frequency under red. And so if we were to have our visible light, then red would be over here on this end and purple would be over here on this end. So it makes sense that it's sandwiched between these two. So the color we see is the wavelength that is reflected off of the object that we're looking at. So if we're looking at this lemon, we see yellow because the wavelength that's reflected off of this lemon is the yellow wavelength. So whatever, 500 or so nanometers of light. Yeah, that's about right. And so every other wavelength of light is absorbed into that lemon. So now we're going to take a quick break, but then when we come back, we're going to talk a little bit more about what we mean by absorb. And we're also going to talk about how our eyes see, and specifically how our eyes see color.